Hi, my name is Jonathan Franco, and today I'm going to be teaching about PLCs, also known as Programmable Logic Controllers. Let's get started. Typically, PLCs look something like this. A programmable logic controller is basically a small computer that can carry out pre-programmed outputs based on inputs and a set of specific rules. They are used in commercial industrial applications to control systems with minimal and sometimes even zero manual intervention. The operation can be a simple on and off control based on a status of input, or a more sophisticated response based on calculations, sequence, and logic. Before PLC, control was carried out via banks of relays. Each relay controlled dedicated inputs and outputs. Based on physical wiring, relays would control other relays to form logic controllers. For example, with a simple AND gate, only when two inputs are energized, and this one does the relay output energize. These inputs could be sensors, or they could be outputs from other relays. To change the operation, the physical wiring had to be changed. So the physical connections had to be altered. If a different response was ever required, these old banks of relays were vast in size and very complex. This is an example of an elevator relay bank, and this is a relay bank from an old electrical substation. As you can imagine, these are not going to be easy to change, and finding faults can be difficult and very time-consuming. With this invention of solid-state electronics and microchips, the command logic part of the banks of relays could be replaced with software logic, and so PLCs quickly take over. PLCs vary widely on their application, but they all monitor their inputs. They make a decision based on a stored set of rules, and from those, they then output commands to automate a process. We often find relays used in combinations with PLCs. The relays can directly deal with the automation tasks and communicate with the PLC. This will reduce the amount of programming required on the PLC, and also free up storage space. PLCs are widely used, for example, when you check a bag at an airport, the bag is given a barcode and enters the conveyor belt. A PLC scans the barcode and, based on a set of rules, decides if the bag is diverted to either the domestic or international route. Next, PLC scans the barcode and decides which city the bag needs to divert to. The next PLC decides which gate is also needed to divert to. And if all goes planned, the bag will arrive at the correct gate. Here are the main parts of the PLC. First, we have the input modules or field sensors. These are the physical connections between the outside world and the PLC. These can be digital inputs such as on and off switches, biometallic temperature strips, presence or motion sensors, even a float switch. These digital inputs can only provide information on whether something is either on or off, and nothing in between for that. We would need an analog input, for example, a simple control knob which ranges from 0 to 100%. This will go through a voltage transformer to give 0 volts at 0% and 10 volts at 100%. The PLC can scale the input to match the sensitivity required for a very accurate output control. It also converts the voltage into current using resistors and Ohm's law. The amount of current, usually measured in milliamps, tells the PLC whether something is performing between on and off. These inputs can be, for example, a thermocouple or a resistance temperature detector. It could be a pressure sensor or perhaps a strain gauge. These voltages or currents are converted into a digital equivalent number that can be understood by the CPU. We will look at that later in this video, so don't worry about it now. Input modules will perform 4 main tasks. They sense when a signal is received. They convert the signal voltage into the correct signal for the CPU. They isolate the PLC fluctuations in the input voltage or current signals, and they send the correct signal to the CPU. The CPU, or central processing unit, is the brains of the operation. It holds the program or software that decides what outputs are required. By applying rules to the input signals, the CPU typically consists of a microprocessor. which does the work based on the input value, and the logic in the program. A memory chip is stored in the program. This will also store the output history, also any faults or alarms. Then we also have the integrated circuits. These can be things such as Modbus and LAN connections, which allow us to remotely communicate with, reprogram, and even monitor the devices. Then there's an output module or field output devices. This is providing the signal to the device we are controlling. For example, a simple indicator light, a solenoid valve, a motor starter, and a variable frequency drive. There are some other parts, such as the battery to keep the PLC alive. In the event of a power failure, there might be a small screen for a user interface to allow some configuration. There will need to be a time clock, a calendar to operate a device at the correct time. And there will also need to be a power supply to provide the low voltage used by the CPU, as well as the input and output modules. The basic operation of a PLC is to perform a pre-programmed output, depending on the input signals. By following a set of rules, the PLC completes the following stages in its basic operations. First, there is the input scan, which detects the state of the inputs. Then the program scans to see what needs to be done. Then it will execute the program logic to actually implement what the rules state. Then it must update the outputs to operate output devices based on the program requirements. Finally, the housekeeping for self-diagnostic, communications update and reporting. The scan time, which is the time it takes to complete all the stages, depends on the sensitivity. The reliance and the system processing time, analog inputs tend to take longer to process compared to more simple digital and on and off inputs. For example, a water tank might have a very fast scan time to 2 milliseconds, and this will prevent overfilling. But a room temperature control can be much slower, perhaps 100 milliseconds. Let's see an example of a simple response. We have a biometallic strip sensor, a PLC, and a boiler. The biometallic strip bends as it becomes hot and cold. We can use it to detect if the room is at the desired temperature, and from the control boiler when the room is at the correct temperature. The circuit is complete and the PLC receives a signal, so the boiler is off when the room temperature drops. The circuit is no longer complete, and the PLC detects this change on the input. It reacts by sending an output signal to turn the boiler on. This is very simple, and we can use the simple relay to achieve this. However, a PLC is better because it has time to function, so it can check the time before switching the boiler on. For example, the building might be empty at nights and on the weekends, so we don't want the boiler to turn them on. The PLC is told the room is too cold. It checks the time and date to see if it's allowed to turn on, and then, based on this, decides whether to turn the boiler on or leave it off. Sensors on the input. The thermostat tells the PLC room is too cold. The PLC will check the time to ensure it is allowed to turn on the boiler. And now you can also check to see if the room is occupied. For example, there could be a public holiday that isn't listed on the calendar. The building is empty, so the boiler doesn't need to turn on. Let's look at some more complex examples. In many commercial buildings, the heating or cooling system will use a control strategy. Known as the optimizer, this learns over a period of time how quickly the building heats up or cools down. It starts the heating or cooling system at the optimal time, before the building will be occupied. For example, if the staff are due to turn up and start work at 9 a.m., the heating system knows that it will need to turn on at 7 a.m. to ensure that the rooms are all at the correct temperature. Let's say the system has a PLC with a optimizer software installed. This controls an actuator valve from the heating system. This also has 2 pumps, which are set up in duty and standby configurations, so only one pump runs at a time. The PLC will decide which pump to turn on. Based on whichever has the lowest number of previous run hours, the PLC will monitor a flow sensor to detect if the pump turns on. When told to do so, if the pump fails to turn, the PLC receives an alarm and it will cut the power. It then tells the other pump to start. However, before the heating system and pump start, the PLC would check the clock. Should the heating turn on today? And if so, at what time will the building be occupied? The clock says yes. The scheduled time is 9 a.m. The PLC then checks the current temperature of the room and calculates the difference between this and the desired temperature. It then checks the outdoor temperature to calculate how long it would take to heat the building up. Because on a very cold day, there will be a greater heat loss, and so this will take very long. From this, the PLC calculates what time it needs to turn on the heating system so that the building is at the desired temperature ready for 9 a.m. Now let's take a look at the advantages of PLCs. There are many, but some of the main ones are: the control system is stored locally, so in the event of a building energy management system failure, the PLC can carry on working. The connections between the PLC inputs and outputs are made by the software, and not by a lot of physical wires. PLC installations are smaller than hardwire relay banks, but they can still use relays where needed. PLCs are much easier to reprogram. Fault finding is easier and faster. You can also load the same program onto multiple PLC units at the same time to save time. You can also expand the inputs and outputs with more cards. Thank you guys for watching. If you like videos like this about PLCs, make sure to like, comment, and subscribe. You guys can check out these videos up here, and I'll see you guys in the next lesson. Peace.